Alrighty, welcome back to another LeetCode medium problem. We're looking at 207 course schedule. We're doing our usual thing. We're going to try to find a solution before we write a line of code. So let's understand the problem and see if we can come up with a solution. I have solved this before, but quite some time ago. So I hope I can solve it again without looking at the answer. So let's see. So there are a total of num cursus courses, right? And that you have to take. The courses are labeled from 0 to num courses minus 1. You are given an array prerequisites where prerequisites index I is a two-dimensional array that contains information that you must take course BI before you can take course AI. So this is kind of a dependency. So I have to take BI before I can take AI. Okay, for example, if the pair 0, 1, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return true if you can finish all courses, otherwise return false. Okay, this immediately sounds like a graph traversal problem to me, where we are just giving all of the edges. And what are some of the constraints? Okay, so there's a limit on the number of courses. For our space and time complexity analysis, we're not going to care about that because we're interested in the asymptotic runtime. The number of prerequisites is also limited. But we know that in each prerequisite we have exactly 2 entries. And all entries are valid course numbers. Okay, great. Oh, and what's more is all pairs in our prerequisites area are unique. So that's good to know. It doesn't say anything about circular dependencies though, right? You could have a case where, oh, there you go. That's actually an example. So yeah, let's look at the example. So if you have 2 courses, you have course 0 and course 1. Course 1, wait, what was the order? Well, you have to take course 0 to be able to take course 1, but also you have to take course 1 in order to be able to take course 0. So that's a circular dependency. So you cannot complete the courses. Right, so this is impossible. Cool. And the other example is simply prerequisites. You have to take, so you must take course, the last one before the first one. So you have to take 0 before 1. To take course 1, you should have finished course 0. So this is definitely possible. Okay. Yeah, interesting. So yeah, I would like to approach this like a graph problem. The question is now, how are we going to construct this graph? Right, and we have to find the entry points. Like we have to find courses that don't have any dependencies. What if we, well, is it guaranteed that we always have all of the courses? Yeah. So num courses tells us, what are all the courses that exist. I guess what we could do is, so I'm thinking about how to represent this graph, right? I think we will have to traverse all the prerequisites, and then we get our courses A and B. And maybe we keep a dictionary that contains a list of all the courses that must be completed before we can do a particular course. So if we have, well, let's say a dependency dictionary, right? And that one basically has a course and it's dependent on courses, on multiple courses. So I don't know, course 1, course 2, and so on. And this could be maybe a set, right? And then we try to find courses that don't have any dependencies. That means we can take those first. And we can remove the courses that we are able to take from the sets of all the other courses where they're contained. So we probably need another dictionary, a reverse dependency dictionary that tells us, well, but basically maps it in the other direction that reverses this. And what we can then do is, yeah, we just maintain a queue of all the courses that have no dependencies. It's kind of like, you know, when you do a graph traversal, you can start at one point, but you can also start at multiple points at the same time. It's similar to the breadth first search, except that your starting points are at different locations in the graph. So you try to expand from each one. Yeah, I think that's what we're going to do. That's the approach I'm going to go for. I'm not sure if I could explain it well, but I hope the code will show that. And this approach will require that we visit each node once at least. And but also we need to store all the edges of n. So since it's a graph problem, let's talk in terms of vertices and edges. I think we're going to need time and space linear dependent on the number of vertices and the number of edges combined. I think that's what we're going to need. And the number of edges, by the way, where well, edges is of course length of our prerequisites, and vertices is basically the length is num courses. Yeah. Okay. So yes, so we're going to need a queue for our processing, and I like to take a deck for that. That just makes the coding a little bit simpler, because it allows you to process elements in the first in, first out kind of fashion. And yeah, and we should probably also use a default dictionary dict. That'll make it a little more convenient for us to create, you know, these hash maps that I talked about first. So we have a processing queue, and we're going to process that queue for a while. So this is going to be for our graph traversal. And when we are completely done, we've processed everything, we have to return true or false. I'm not sure yet if we can return true directly, but we'll see that in a second. But we first need to build our little map, right? So we have to iterate over all of the edges. For edge in prerequisites. And so this is B comes for A, right? So this is so edges from edge is the second value, to edge is yes. We have that. So that means when you completed course from edge, when we completed B, then we can take A, right? To take A, we have to complete B. Yeah, that's what that means. So this is actually a directed graph, right? Cool. So now we need to maintain our dependency list. So this is how should we call this? Dependencies is a default dict, and it's going to be a set. So, and now we just update the dependencies. So dependencies, in order to do A, we first have to do B. So that's a dependency. And the reverse dependency is, well, the other way around. Maybe we should name that differently. How should we name that? So we're storing in the reverse one, we're storing. Wait, I got the first one wrong. So sorry, I'm a little bit slow today. So let me just check this again. So in order to do to edge, we have to do from edge. From. Okay. Maybe we should call this before and after. So before and after, and before and after. So before parent, maybe we should call this parents. Parents. So the parents thing contains. No, wait. This is children. The children lists all the courses we can take after completing the before. And parents. Maybe we should name it this way. Parents. Parents lists all the courses that we have to take before we can take the course. Right? Yeah. Okay, cool. I think that should be it. Now we need to find, okay. We need to find out which ones do not have any dependency. So if there's no edge, so if we have, well, we might have missing entries in parents, right? So we know that we have num course, so we need to make sure that every entry exists. So maybe we don't use a default dict, maybe we just initialize all of them. So course set for course in range num courses. Yeah, I think that's what we should do. We should initialize it, give it a set. We don't need a default dict. So that ensures that we have all of the courses in here. And some might have an empty set, right? But that is fine. All right, so now in order to build our deck, we have to iterate through all of them for course and courses. And now we have to check if, well, the course has no parents. That means that course doesn't have any dependencies, so we can add it to our deck. Yes, and so that's how we seed our graph traversal. And now in our graph traversal, what we do is we iterate over all of the nodes that are currently in our FIFO. So 4, and then we just iterate over length, in range, length, length of the queue. And if you've seen the other videos, you know that I really like this pattern because this gets evaluated only once, even when we start to modify the deck inside the for loop. The length is evaluated once, so we can be sure that we process exactly as many, however many elements we have in our deck. So we pop out the node. So we say course equals q.pop left. Pop left removes the first element from our first in, first out data structure. And now that means we can actually take this course. Awesome. So what we have to do next is now we have to iterate through all of the children of this course, which means all of the other courses that are dependent on this one, on us completing that one. So for child in children of that course, and might be empty, there might be none. That's fine. And now what we do is we get the child course and we basically remove our course from the child's parent. Child, but remove, because we're dealing with a set, course. And we have to also check whether now that that set is empty. If not, so if it's empty, we could do if length equals 0, that means the child has no more dependencies. So we can add our child to our processing queue. And that is then how that works. Now, one thing that we have to be careful with is cycles, right? So we could run into a cycle here. Could we? So what would happen if we ran into a cycle? Let's just play through this real quick. So if we run into a cycle, well, if we run into a cycle, so this one, for example, our queue would never have anything to begin with. So this would never execute, right? So I guess at the very end, we need to check if actually if we've completed all of the courses. And one way to do that is, of course, to check these dictionaries, or yes, to check all of these dictionaries. Or could we just keep track of the courses that we completed? Now I'm thinking, if we do that, can we be sure that we never count a course completion twice? Well, yeah, I'm not 100% sure. That's because I have a little bit of a cold, so I can't really think that well. But I think, yeah, we need to examine the condition of when we return false and when we return true. So this one will traverse all of the nodes. If we keep track of all the courses that we completed. And since we already have this space complexity, and space. Since we already have the space complexity, doesn't really matter if we use another, well, completed maybe set. Completed set, and then we check return the length of completed. Is it equal to num courses? Right. And if we complete something, we basically add it to our completed. That's what we could do. That's an easy way to keep track of that. It could also be that we just, increase a counter here, but I'm not 100% sure. So just to be safe, I'm just going to use a set, because if we add on something multiple times, it doesn't really matter. So yeah, let's just see if we have any syntax errors here. We don't have any syntax errors, and actually the test cases pass. Now the test cases are not very comprehensive, so chances are that we could still run into an issue, but I'm going to submit it to see what the LeetCode tells us. Oh, I'm surprised. Okay, so that works. Nice. Cool. I'm just curious. I just want to know whether completed, maybe if a counter works as well. Completed. It plus equals 1. And if we submit that, that works well. Okay, cool. Okay, that's good to know. And yeah, let's check out other people's solutions. What do they have? Beats 100%, DFS, Python 99%. I really wonder, why do they care about the actual, like the runtime milliseconds? Nobody cares about that. Come on. At least not for interviews. Maybe that's why. Breadth first search for cycle detection, which is basically what we're doing here. Checking if loop exists. Okay, yeah, you don't have to do that. You just have to engineer your algorithm the right way. Nobody has a runtime analysis here. Hans algorithm. Python, okay, same space and time as we have. In degree, okay. Okay, so this is interesting as well. So, so instead of actually having the elements, the dependencies in the list, here they just count how many dependencies exist. So, and when they then traverse the thing, they just remove those dependencies. And what else? So they use S as the queue. So they place everything into the queue, I guess. Oh, well, it's kind of the same approach. So yeah, they kind of do the same thing. They have they have one dictionary and one array, right? And they exploit the fact that we know how many courses there are. So they're sizing the array in the correct size. And we are sizing our hash maps, right, instead of an array. And then they basically only keep track of the in degree. They increase the in degree for our nodes. So we use the parents hash set for that, for where they use the in degree and the count. And then they initialize their queue the same way we do, by checking where's the in degree 0, where do we not have any parent nodes. And I guess L is the number of completed course, or is the list of completed courses. And then they do something similar as to we do, but they don't use a deck, they use a simple stack, which is fine. You can also use a stack, doesn't really matter. And they pop out the course, and popping out the course from the queue is equivalent to completing it. So they add it to their list L. And well, actually they could use a counter instead of L. They don't need a list like we just figured out. Yeah, but well, you tell me which one is harder or easier to read. Just terrible in variable naming over here. But yeah. Anyways, I think that concludes this video. And yeah, give it a shot yourself. I think it's gonna be fun.